Okay, any questions? So, what are we doing here? What are we doing here? There are a lot of people today. So, what we are doing is to figure out how do things mix. So, we are continuing to talk about mixing of two components, A and B. Last time we showed, and we came up with a few models for this, okay? So we said, so our first model was called an ideal mixing model. The second model was called a regular mixing model. And probably right before Thanksgiving, I will talk a little bit about what's a real mixing model, but the regular model itself is very, very powerful and it can do a lot. And a better way to, last time I wrote delta G first, and which confused some of you. So the first way to really think about it, the better way to think about it is what happens to the delta U, delta H of mixing in each model, what happens to delta S of mixing in each model. This is what you define in every model. The delta mixing G follows directly from delta H minus T delta S. So you don't have to worry about you don't have to specify what will be the free energy of mixing in a model. That comes from the first two things, how you specify it. So in an ideal model, we said there is no enthalpy of mixing. Everything is an ideal gas type particle, so we don't care. While this one came out to be RT summation xi ln xi. And I wrote the general form where I could go from 1 to k if you have a k component system. Okay, if you have just two component, it is xa ln xa plus xb ln xb. So some of you asked me after the class, why did you keep the same entropy in the regular solution model? That's just an approximation I am making. Anytime I am devising a model, I go one step further and make my model increasingly more complicated, right? A lot of chemistry and physics. Those of you who are interested in doing PhDs, how many of you are still thinking about doing PhDs? I see quite a few hands. There is still hope. Good. I'll talk to you when you're a fifth-year graduate student. You know, like, oh. So PhDs and science is all about building models systematically. Go ahead. Huh? Yeah, it's minus R and there should not be a T. It should be minus R. Correct. It has to be positive. This takes care of that. So sorry about that. So in the next model, we say we are going to keep the same entropy of mixing as the ideal model, but we will allow our enthalpy to become more complicated. And this was done by introducing an enthalpy of mixing that depends on the, and I should write maybe small x for the mole fraction, depends on the mole fraction of each species. This is the simplest. So you can imagine more complicated models, right? One of the way to do it would be to, so in a real model, both of these will become more complicated. And I will talk a little bit about that later. But right now, let's just focus on the regular solution model, okay? So in regular solution model, we therefore have delta mixing of G is going to be omega xa xb minus T delta S. So that's going to be plus RT. And I will write it down for a binary model. So I will get rid of the summation, just write down explicitly what it is. Xa ln xa plus xb ln xb. This term here is what we are going to look at today. So we are going to do two things. We are going to do two things today. So today, we will look at equation one for two components, but only one phase when they mix uniformly. And equation two, and then we will move on to equation one for two components and two phases. And that will be to what pretty much, we still have a couple of things more left to do with phase diagrams, but then we are nearing the end of the phase diagram. But what I will show to you that if you can understand B, which is how does this look for two components in two phases, you are actually empowered to look at all complicated phase diagrams. Okay, and the topics that are going to come after this are going to be something called lever rule, which is to read a phase diagram and actually make sense of what is the mole fraction of different components in different phases. Right now, it might seem like I'm just blabbering some random words, but it will all hopefully start to make sense. When I talk about things that are coming too far into the future, of course, it's not going to make too much sense. And then I will talk a little bit about ternary phase diagram and how to read those, just a little bit. Okay, so let's talk about first our equation 1 for two components in one phase. So this is, I think it should be a lot of fun. Type 1 even. So we have delta mixing G is equal to omega XA, and sometimes I write small x, sometimes I write capital X. I'm sorry for that, I keep forgetting. So in a two-component system, what can we say about XB and XA? How are they related? Go ahead. They add to 1, right? It's a two-component system. So XA plus XB is equal to 1 because they are mole fractions. We are not talking about the total number of moles. We are talking about the mole fraction. Therefore, XB is equal to 1 minus XA. Therefore, delta mixing G can be written as omega XA 1 minus XA plus RT XA ln XA. And here I'm going to keep the XB ln XB. We have already plotted it in the past. So you can substitute XA. If you did the practice problem, you probably did that. You did substitute 1 minus XA even in this term over here. But let's look at this one. Specifically, let's look at this one. Let's ignore the omega. Omega can be positive, omega can be negative. Let's just look at this term and try to plot it. Okay, so let me make a plot where, so I'm trying to plot y is equal to x multiplied by 1 minus x. Okay, so I have my y-axis and I have my x-axis. How much is this going to be? And I'm interested only in x going from 0 to 1. The mole fraction cannot be smaller than 0 or more than 1, right? So at x is equal to 0, what is the value of y? Cosmo, what do you think? Yeah? 0. And how about x is equal to 1? Also 0. Is it ever going to be negative? Why not? Because x is always positive and 1 minus x is also positive. We have restricted the range, right? So it's always going to be positive. And here is a trickier one. Thanks, Cosmo. If it's always going to be positive, which means it's going to lie in this part, how many maxima will it have? 1 or 2? Huh? 1, right? Yeah. It's a quadratic, right? So if you do y is equal to x, 1 minus x, this is something which is in the math module, in the first math module itself. If you do dy by dx is equal to 0 for a maxima, which means 1 minus 2x is equal to 0, or x is equal to half. What is the other condition for a maxima? D square y by dx square should be negative. You can go and check that. D square y by dx square everywhere is minus 2. So definitely this is a maxima. So it will have one maxima at half, and it's going to look something like this. So keep this curve in mind. And now so those of you who came late, we derived the mixing free energy for Gibbs, the Gibbs mixing energy for a regular solution model last time. And we are going to plot it now for different values of omega and different values of temperature. And 3 of these 4 cases are going to be very simple. One case is going to be extremely interesting, I think. So let's look at it. So let's plot equation 2 for 4 different cases. Okay, First case, we will do omega negative and high temperature. Second case, we will do omega negative and low temperature. Third case, we will do omega positive and high temperature. And fourth case, which, as I said, is actually quite interesting, is when omega is positive and the temperature is low. So let's work through it systematically. Let's start with the first one, which is omega negative and high temperature. And what I'm going to do now is to make 4 figures where I will be plotting everything. Okay, and in each of these, I'm going to have a line corresponding to 0. This is my 0 line. And I will plot things. So this first one is omega negative and high temperature. Okay, now so we want to plot, what are we trying to plot? We are trying to plot the delta H mixing, which is this part. Then we are trying to plot this second part, and then we are trying to add it up, okay? And that will give us delta G mixing. First part, XA, we saw that XA multiplied by 1 minus XA is always positive. But now it is multiplied by an omega, which is negative. So what does it mean for delta H mixing in this first part? Will it be positive or negative? Stella, what do you think? Negative. Confident? Confident? Yeah. Okay, cool. Stella is confident. Okay, then I'm going to ask more questions to Stella. So it's going to look something like this, okay? It's the same curve that I drew over here, multiplied by omega, which is negative. So it just goes on the other side. So this is delta mixing H. Okay. Now, Stella, do you remember how will this second term look like? We know that R is positive, right? It's a gas constant. Temperature is positive, it's a gas constant. XA is positive, it's a mole fraction. How about log of XA? Negative, because XA is smaller than 1. So the whole thing will be negative. And we did this last time. It will be negative with a slope that is minus infinity at the both ends. So this delta, so this is not delta S mixing, this is minus T delta mixing S, okay? This whole thing is minus T multiplied by S. Thanks, Stella. So now we are gonna add both of these to get the delta mixing of G. I want someone else who is, I want someone else to answer for me, not the usuals. Alex, what do you think? When I add these two, what's the delta G going to look like? Can it ever be positive? Are you sure about it? I'm adding two things which are always negative. No, right? So, but more importantly, will it, so okay, it will be always negative, but can it lie over here, or does it have to always lie down below? It's a sum of two negative things, right? It would be always below. Good, thanks. So, and I'm going to use a red curve for that. So in this case, the delta G mixing is going to look something like this. So at high temperature, if the regular solution parameter omega is negative, things will always like to mix. And remember what we talked about the omega parameter last time? It tells us how much is an AB bond preferred over AA and BB, right? So if you have high enough temperature, an AB bond is preferred over AA and BB, things always like to mix. It's the spontaneous direction anytime. So this is XA is equal to 0. This is XA is equal to 1. Sorry, left side is XA is equal to 1. I should have marked that. and this is Xa is equal to 0. So this picture is telling you something simple. Anytime you add a little bit of some other, the B quantity, you start with pure A, you add a little bit of B, it will mix. For example, if you had a solution here and you start adding sugar to it or salt to it, it will not precipitate out. It will keep mixing. And the more you add, the more it will mix. You will never have a problem. So this was when omega is negative. Now let's go to the second case and work through it. When omega is negative and low, any questions about the first case? Stay with me today, please, because if you get lost in this, then today's class and the next class are gonna be, you'll just hate me. You'll be like talking French or Hindi or some other strange language that no one understands. So please stay with me. And if something is not clear, please stop me and ask me. There's no point in me rushing through it. Is it clear? Okay, if it's clear, then let's go to the second one. In this case, omega is negative and now low temperature. If omega is negative and I have changed the temperature, is it going to affect my delta mixing H in any way? Why not, Daniel? It doesn't have any temperature in it, right? This term has no temperature in it. So this term is going to look exactly as we drew in the first case. Sorry. The delta mixing H is going to be the same. The second term will change. The minus T delta mixing S will change. What will happen to it? Will it go up or low? Oh, go ahead, Hannah. Huh? Are you sure? So it will, you are saying that so it will go up, but not curve up. It will not find a dome. It will still have the same behavior. It will just move up a little bit. So in this case, this curve over here, so here you had a bigger gap between both of them, right? Because the temperature was very high. Now the temperature is low. So here, and it's possible that the temperature is so low that it becomes almost flat, but it will not become positive. So in this case, it's going to look something like this. And it's very well possible that it comes and becomes almost flat if the temperature is so low. If you have zero temperature, it will just become a flat line. But the point is, it moved a bit closer. So this is minus T delta mixing S. What is the net effect on delta mixing G? You have answered already. Someone else? You have also answered. Someone else? Andrew, what do you think? The sum of these two, will it be negative or positive? Negative. He's confident. You are, right? Cool. So it will always be negative. And in fact, if the temperature was 0 and that delta S mixing curve became flat, it would still be negative, right? So the big picture here is that if the regular solution parameter is negative, then at low temperature or at high temperature, they will mix the same way, right? If A and B do not like each other, you will always get mixing. Doesn't matter whether you are at low temperature. At low temperature, the enthalpy dominates, right? Because at low temperature, this term just goes to 0. And it says, well, sure, let's mix as much as possible. And at high temperature, entropy starts to play a role. And it says, well, anyway, I want you to mix more. So it's just favorable for things to mix more and more and more, irrespective of the temperature you have. Now let's go to the more interesting case, which is omega less than, now we are going to make omega positive. So what do I mean by that? Omega is positive and we are going to look at high temperature. If omega is positive and high temperature, what does omega positive mean? Omega positive means that A and B do not like each other. If there was no temperature in play, you would rather hang out with the A would rather hang out with the A atoms, B would rather hang out with the B atoms. Just on the basis of potential energy, on the basis of bond strengths, A does not like B as much as it likes A and things like that, okay? So in this case, now let's think about our delta mixing H curve. How will that look like? What do you think? Positive, right? Because we saw this thing is positive. Think about this curve over here. Now you are multiplying it by omega, which is always positive, right? So delta mixing H is going to look something like this. And it should really be symmetric. It should be peaking at x is equal to half, but I'm not very good at drawing, I guess. So this is delta mixing H at high temperature. Let's make this one also for the other case, final case, which is omega positive and low temperature. We know that delta mixing H is not going to get affected by the temperature, right? There is no temperature term in the omega. Of course, in real world, you could imagine a model where omega itself starts to depend on temperature, right? If you really want to come up with a very complicated model, you could make your omega temperature dependent. No one's stopping you, it's just a model. So in this case, once again, delta mixing H is going to look something like this. But now the fun part will happen, and let's work on both of them at the same time. Let's think about minus T delta mixing S. So now I want you to think about this one over here. This has no effect on, omega does not affect this one, right? Is there any omega in this term? It's only temperature dependent. So at high temperature, it's going to look the same as the one you drew over here on the left side, right? It's not going to be affected. So it's going to look something like this. Minus T delta mixing H. And at low temperature, it will again be negative, but it will be a bit closer to the axis. Minus T delta mixing S. Now let's try to sum up both curves and get the final curve. In order to get delta mixing G, I have to sum this black curve with this green curve and get both of them. In the top one, the green curve is very, very negative, okay? It's so negative that it really beats the crap out of this one. And here the slope of minus infinity also matters. Not only is it negative, if you think mathematically, what is the slope of this one at x is equal to 0? If you calculate the slope of this one at x is equal to 0, it's 1. It's not minus infinity. It rises very gradually, right? The enthalpy term rises gradually, while this one drops drastically, because we saw that the slope is minus infinity. Practice problem number 13. So overall, how is it going to look like? This is a tricky one. Anyone wants to answer? Go ahead. It will still have a negative thing. And yeah, correct. So in this case, it's going to look something like this. It's almost like minus T. Oh, wait, I had a typo here. Sorry. This is S. It's the minus T delta mix S. The entropy of mixing dominates, but you're adding something positive to it a little bit, right? So it rises up just a bit. So overall, it's still going to look as minus, so this is delta mixing G. So now if I removed the enthalpy and the entropy from all these pictures, the three pictures, we are going to get to the fourth one in a moment, and I ask you to just compare the delta mixing G. If you did an experiment on a system where all you measured was delta mixing G, would you really be able to tell the difference? I don't think so. It just looks like it mixes more and more. This sometimes becomes complicated when you look at proteins or other chemical systems. It's hard to say how much is the contribution coming from enthalpy, how much is the contribution coming from entropy. The free energy can mix both those things. Now let's get to the very interesting fourth case. What's going to happen in this one? In this case, we know that the green one, and this is why when I told you the slope of minus infinity matters a lot last week, and I was rambling like how it's my favorite equation, it plays a role over here. So we know that this thing So, one more. This thing, sorry, my colors are getting messed up. Over here is again going to rise gradually because it's a nice quadratic function, while this over here is again going to drop drastically. So when you are at either end, the entropy of mixing will dominate. You will drop down like, I don't know, drop down, basically drop down like me trying to swim with a bunch of like stone or something tied to me, right? It will drop down very, very quickly. Or just me trying to swim. I'm a terrible swimmer. So it will drop down, and let's draw how it will look like. So it will look something like this at the either end. But the question is, will it always be negative in this case? No, in the middle, something is happening, right? Delta H mixing is more positive. So it has to rise up, and you will get a complicated behavior here. It's going to look something like this. It will have a bump in the middle. Go ahead. Yeah. Go ahead. It could become positive. It could stay under, it doesn't matter. So this thing, this bump could also be positive. That really depends on the precise temperature you have, right? And the precise value of omega. But the point is, you don't have a monotonic, none of the curve is monotonic. You don't have a simple curve. You have a curve with a peculiar bump in the middle. And this is the first time we are seeing such a bump. And this bump matters a lot for phase diagrams. What this bump means is, and this is really, really practical. Let's think about oil mixing with water. When you start adding, is that a good example or do I have a better one? Yeah, when you start adding oil to water, let's say you have, or water to, yes, oil to water. You have a bunch of water and you started adding oil to it. What will happen initially? They will mix, right? You won't be able to tell what's going on. But at some point, you will see these oil droplets starting to emerge where it's not mixing. The oil will maybe come to the surface and things will happen. So that's what happened over here. It will start to mix. At some point, two phases emerge. And the composition of two phases is given by these 2 points over here. And we will study why those 2 points matter. It is called the common tangent construction. But so far, I want to see that something complicated happens when A does not like B as much as A likes A and B likes B, and the temperature is low enough. If the temperature is high enough, so let me write it down on this page. I will give a moment because these were a lot of diagrams to make sure people have copied things correctly. So everyone okay? Can I move? Anyone does not? Yeah, go ahead. Yeah, you're correct. So, but then I won't be able to draw it correctly, right? So what's your name? Alan. What Alan said, you should really be drawing over here, right? But that's going to be hard to read. So, okay, I will draw it for Alan. So this, I will draw Alan's photo. And his glasses. That's Alan. So this is a zoomed in version. Okay. In reality, it should be in between. You're absolutely correct. But then it will be hard to see. So that's a zoomed in version. Okay. So let's summarize this. We have talked about omega. Omega negative means that AB bond favored over AA and BB. And the thing to remember about bonds is that a bond strength is only a zero temperature property. A potential energy curve has nothing to do with temperature. And in chemistry, this it's kind of sad that a lot of even very, very, very good scientists, even like Nobel Prize winning level scientists for that level of work, sometimes totally ignore the role of entropy. Whatever conclusion you're drawing from just bond strength, and it's easy to get bond strength by doing something called density function theory calculations, which is quantum mechanics. Someone named Martin Karplus got there have been at least 2 Nobel Prizes in this field over the last 20 years. And what it does is to allow you to calculate, not Martin Karplus, but someone named Walter Kohn. So you can get the bond strength from doing 0 temperature quantum mechanical calculations. But that is just 0 temperature, right? As we saw, even if you got the bond strength, even if you were able to calculate the precise value of omega, depending on the temperature, things might change. Here we had a simple model for entropy, which is XA log XA plus XB log XB. Clearly, for complicated systems, this entropy model wouldn't apply, right? It would become very, 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 very complicated. And that's where chemistry, computational chemistry becomes a bit hard. But let's get back here. So we have omega negative, which means AB bond preferred over AA and BB. In this case, high T or low T mixing is spontaneous, which means that at either temperature, at either high T or low T, your XA is equal to 1, XA is equal to 0. If I am plotting the delta G mixing, it's always going to look like this. It's always favorable to mix. So instead of oil and water, if you had 2 other components where they really like to hang out due to their bond strengths, you will never be able to get phase separation. They will just keep mixing uniformly. Can anyone think of 2 chemicals which keep mixing uniformly at all concentrations? Go ahead. Well, there will be alloy systems. There will be material systems, maybe copper, zinc, iron, or something like that. But I would like you to think about more liquids which can keep mixing. Huh? Which hydrogen peroxide and why? So if both are very polar, then they might keep mixing. If both are very non-polar, then they might keep mixing. The problem happens when one of them is polar and the other one is non-polar, right? That's when you start to have problems. Now, when we go to omega positive, this means that AB bond is not favored over AA and BB. So if you had a 0 temperature system, the bond strength of AA and BB is deeper. They form stronger bonds than just AB. So in this case, if your temperature is low, entropy doesn't really matter, and once at low temperatures. And once again, you get a curve that looks something like this. But if you had high temperature, then you start to get a competition. Did I do it wrong? I did it wrong, sorry. If it's high temperature, then entropy dominates, and it doesn't matter that A, B did not like each other. Entropy says, shut up, I want you to mix. I want you to get chaotic and completely get random. Entropy takes care of everything. But once you get to low temperature, the power of entropy starts to reduce. And at low temperature, you get this interesting behavior where you start off mixing, but then you might decide not to mix. And this curve can very well go above the x-axis and things like that, okay? In general, for any energy, the absolute value typically does not matter, right? We are talking about delta G, right? It's all about change in energy. That's why I was not too fussed over whether it crosses the axis, but it's a good point that Alan made. So this is XA is equal to 1, and this is XA is equal to 0. Cool. Everyone feels like they have become wiser today, right? I mean, that's the point of going to, I don't know, doing PKM. Like at the end of the semester, you will feel like, wow, I know a lot. It's a good feeling, you know? Go ahead. Oh yeah, everything can change depending on omega and temperature. Go ahead. I'll come back to it.
Possible that, like, it does get negative, but for some brief period of time,
you are fighting the slope of minus infinity. So it will have to be some mathematical limit. Okay, it's possible. So yeah, Daniel, what was your question? One more question. You can do a bunch of things. I'm glad to see that at least some of you are getting excited. This simple formula, this is why I like it so much. You know, this omega xa xv plus rt xal and xa plus. Hopefully I've showed you how it can reach to such rich phenomenon, right? It's a simple algebraic equation with one quadratic term and one logarithmic term, and it can lead to so many complicated things. Okay. So this is kind of the hardest part. If you got this, what I'm going to do next might sound like it's going to be even harder, but it's actually not that hard. So this was when we had only one phase, right? We were just talking about one curve, how it behaves, how it moves. But now I can move, and I'm going to introduce this and really resume from this page the next time again, because this was not a lot of material, but it's a different way of thinking. So now we are going to think about, again, a two-component system. But this time, two different phases. Okay. For example, this could be liquid and vapor. We will do everything in the context of liquid and vapor. So what this is going to do for us is going to allow us to construct a liquid vapor phase diagram. You can do the same thing for solid vapor. You can do the same thing for solid liquid. For other phases, the same machinery will apply. We are not going to do all of that because this is not a phase diagram class. This is PCAM, and we will do this one and try to see how it looks like. So the net result of this, I will draw you the final result that we are going to prove how it looks like. A liquid vapor phase diagrams looks generally something like this. So this is XA is equal to 1, XB is equal to 0, XB is equal to 1, XA is equal to 0. So our XB is increasing in this direction. And this over here is temperature. So we are talking about a temperature composition phase diagram, and we will prove that it's going to look something like this. This over here will be liquid. This over here will be vapor. This is not, and what will happen in the middle? Liquid plus vapor, two-phase system in the composition phase. So when we saw the one component water diagram, remember the liquid plus vapor was along a line, right? But now we have a two-component system. So you can go and prove that in this case, the degrees of freedom for Gibbs phase rule for liquid plus vapor becomes 2. So you don't have it along a line. It happens along an area. This is the simplest phase diagram for a real material. This is extremely common. It shows up for a lot of materials, and we will try to understand why it looks like this. It might not always be downward sloping. It could very well look something like this one. It could be upward sloping also. For example, if I just change the axis, right? If I make this the B axis and make the right one the A axis, it will become upward sloping, right? But this leaf type shape is very universal. Of course, it gets very complicated. This, oftentimes you will find diagrams where things look like and you'll be like, what did happen here over here? But if you understand what we did over here for how this bump appears, and you understand how this liquid vapor region appears, you will be capable of understanding all these complicated phase diagrams. You will have no problem in understanding it. Okay, so next time we are going to study this. And in order to study this, we will think about the Gibbs free energy of the vapor phase and the Gibbs free energy of the liquid phase. And we will show that at very high temperature, the vapor always has lower free energy than liquid. At very low temperature, the liquid always have lower free energy then, and this is at a constant pressure, okay? At very, very low temperature, the liquid always has lower free energy than vapor. In the middle, funky things happen. And that's what we will study next time, okay? So I'm not gonna push through it because what I want you to do today is to go back and think about this curve, make sure you understand this type of construction that we did. Next time, in order to do this, we won't have to use the regular solution model. We will be able to do it for, so we are doing this for two component system, which is fully miscible. Miscible is not written as M-I-X-A-B-L-E like mixable, it's written as M-I-S-C-I-B-L-E. So it's a fully miscible two component system. If it was not fully miscible, then we would get more complicated diagrams. So, and you can go and read up on this. Atkins has a chapter or a section on it. So come ready to understand this. We are going to do this, then we will understand this Maxwell common construction rule. And yeah, the semesters. So what else do I have to tell you? So we have a class on Wednesday. We don't have a class on Friday. Please use that time to set up your first meetings to go over the papers. In every team, I'm sure there will be some arguments over which paper to study. Many of you will be tempted to just take the Maxwell's Demon paper because it doesn't have many equations. That actually might be the hardest paper. So be careful. The one with the most number of equations, which is about the core of the Earth, in some sense might be the easiest paper. And it's important to keep in mind, I do not expect you to understand everything in every paper. I read research papers all the time. And do I have some paper here? No, I could have shown you. Half the time I don't understand half the thing. And it takes me a lot of time to go and understand it. So it's okay to say you did not understand everything. You're not expected to understand everything, but work through it. And then we will have one class next week. And yeah, if you have any questions about the midterm, please send me a Slack message.